Hello everyone, welcome back to the latest lecture session. In the last session, we looked at a couple of problems relevant to lime soda softening. So let's go forth from there. Lime soda softening, what is it that we are trying to do? We are trying to remove hardness. And what is the principle here? The principle is dissolution and precipitation. When does precipitation occur? When you have solids or such, or whether the relevant compounds being supersaturated. So then they will not stay in the solution in the dissolved phase only, but they will also precipitate out. So in that context, we looked at applying the principle of precipitation. Why I mention this now is that while or after we finish discussing this lime soda softening, we will move on to another aspect. There the principle is going to be different. So we have to just understand the principle here. Here we are trying to remove calcium and magnesium by precipitation. So following up with what we discussed last time, conventional softening basins, right? So this is what they look like. You can see the flow and such. Yes. So paddle flocculators, we saw this with respect to flocculation and such, right? This is what they look like, and we obviously looked at the design, the width, the length, the spacing between them and such, and how many per particular shaft. Yes, this is something we looked at. And parallel conventional flow settling basins, this is one other way or one other aspect. So typically rectangular, long and narrow is something that you want. Yes, but then the space beside will be an issue, right? You can't really use the space beside it. So again, different advantages and disadvantages, but with respect to the theory, these rectangular, long and narrow, if you can channel them into narrow channels anyway, that they are the best for sedimentation, right? So conventional softening basins, there are three kinds: single stage, two stage lime treatment and split flow treatment. So single stage lime treatment, we looked at this in the context of the example that we solved in the previous class, right? So here I guess I am providing the relevant information, some of which was also presented in the previous session. Here it is single stage lime and two stage lime, right? That is pretty much explanatory. But what are my objectives here? Here I am only trying to remove the calcium, that to the one that has or that is associated with the carbonate hardness, right? But here I am also trying to add enough lime such that the magnesium is also removed, right? So if the magnesium is also removed, typically you will add, depending upon its association with non-carbonate hardness, you will add excess lime, right, say, right? Or even with carbonate hardness, I guess. So for that you will need to be able to add the relevant soda or CO3 2 minus to precipitate out your calcium, right? To precipitate out Mg2 plus, you will raise the pH by adding CaOH twice. Yes, and if there is not enough carbonate in the system, the Ca2 plus will now add to the hardness. You are replacing Mg2 plus hardness with Ca2 plus, especially if there is no carbonate in the system. So then you are going to add a source of CO3 2 minus, right? So that's the relevant aspect. So we will look at how to go about it and such. So single stage, right? So it's under softening. Why? Primarily I am concerned with calcium that's associated with carbonate hardness. I am not really concerned about magnesium. Two reasons. One is that the magnesium associated with the non-carbonate hardness could be pretty low. So that's when I am going to achieve or try to look at only this aspect. Again, right, it's under softening. So you will always have some magnesium hardness, which we are not even trying to remove. So what do we have? We have raw water from the source, and we are primarily concerned with the calcium associated with the carbonate hardness. Yes. So here what is it that we are trying to do here? We know that it is in Ca2 plus and HCO3 minus, right? But HCO3 minus, I want to raise the pH such that it transforms to CO3 2 minus. Then Ca2 plus and CO3 2 minus, they will precipitate out as CaCO3, the solid. Yes, to be able to achieve this rise in pH, I am going to add lime, right? So that's what I am doing here, lime slurry, and then flocculation and clarification, and then the relevant sludge, which is CaCO3. Some of it we recycle, as I mentioned, to provide the surface area for the particles to, or for the relevant crystals to what do we say, adsorb on and develop crystals, right. So, you are going to bypass that nucleation step, which is a pretty rate limiting step out there, let us say, right. Not bypass, I guess you are going to try to fasten that. So, that is one aspect. So, and then why are we adding carbon dioxide? After increasing the pH, right, let us say to 10.5 or such, you can't what do we say, distribute this water to the relevant population, you need to bring down the pH. So, there are different ways to bring down the pH, HCl, add strong acids or H2SO4, right, but obviously we are only looking for H plus. So, HCl yes, H plus and Cl minus, but Cl minus will add to the total dissolved solids, right. Same case with SO4 2 minus. So, I want to add something that will what do we say, provide the required H plus, and also the relevant anion is something that I would prefer to be present in the water. So, what is that? It is nothing but adding H2CO3, and how are we going to achieve that? By adding carbon dioxide gas, it equilibrates with the carbon dioxide in the aqueous phase, it equilibrates with H2CO3, right. H2CO3 is an acid, and depending on how much you are going to add, it is going to, what do we say, stay as HCO3 minus, or well, it will not stay a lot as CO3 2 minus, but you know this is the equilibrium. So, you know that you can release H plus depending upon the pH and pK of the system. So, HCO3 minus and CO3 2 minus, you know that they will add to the relevant alkalinity of your solution, and also they are good buffers, right. So, that is one aspect why we will choose carbon dioxide to bring down the pH. So, that is why we have recarbonation, right, and then depending upon the relevant suspended solid concentration left after this, you are going to have media filtration. So, this is what we have under softening. As mentioned, we are not looking at magnesium hardness, we are trying to add lime to increase the pH. Flash mixers are used because mixing with a conventional mechanical mixer will cause precipitation on the blades itself and resulting in dislodging and release of CaCO3. So, that is one practical aspect to keep in mind. Usually softened to final hardness, so hardness is 7 to 100 as CaCO3. So, that is something to keep in mind. We are not removing magnesium, and also even after removing most of the calcium, you know that at equilibrium you will still always have some calcium. So, in general, if you are fine with this level of hardness, that is what we are looking at, and this level of hardness is acceptable to most households, let us see, right. So, two-stage lime treatment, let us see what we have. So, here we have excess lime treatment, earlier it was only lime treatment, here we have excess lime, right. Why do we add excess lime? Lime is nothing but, at least the form that we wanted, is CaOH twice. We add it to bring out, or you know, not bring out, transform HCO3 minus to CO3 2 minus, and then bring about precipitation of CaCO3 solid, fine. Why will I add excess? Because if I want to precipitate out magnesium, I can do that in the form of magnesium hydroxide, the solid. Yes, for that I need OH minus, right, 2 OH minus, let me write the 2 here, right. So, for that I need to increase the pH, and that is what I am going to do, I am going to add the excess lime for that, right. So, that is what it refers to. So, that is why we have precipitation of both CaCO3 and magnesium hydroxide. As we know, to remove magnesium hydroxide, the pH has to be considerably high, around 11, 11.5 depending upon your relevant system. So, it is a bit too high, right, and I do not need this high level of pH, and also now I am done with removing magnesium, but I added calcium because in this lime I have Ca2 plus and 2 OH minus, right. So, 2 OH minus was consumed by magnesium, but I added calcium. If there is not enough carbonate in the system, I need to add carbonate, so that this Ca2 plus will again precipitate as CaCO3, the solid. So, two ways to add carbonate, one is adding soda ash, let us say, right, Na2CO3. So, for the source of CO3 2 minus, but again Na plus, you do not want to increase the TDS unnecessarily. Another way is keeping in mind that you do not really need a very high pH of 11.5 to precipitate out CaCO3, around 10.5 or such is good enough, right. So, if I add carbon dioxide, it can achieve two purposes, decrease the pH slightly and also add some CO3 2 minus in the relevant process, right. CO2 will, depending upon the pH, lead to release of CO3 2 minus, which will thus cut down on the requirement or the amount of Na2CO3 required. So, that is what we are doing here. Here I am removing the calcium carbonate hardness and then the magnesium hardness, and then I am adding carbon dioxide to add some CO3 2 minus and bring down the pH slightly to around 10.5, and then I am going to add soda ash, right. So, first stage recarbonation. Why soda ash? Because I have calcium from this excess lime treatment. Where is this excess lime? And so, for that I need to add CO3 2 minus, that is why soda ash is being added. So, then what do we have? We have CaCO3 being precipitated out. So, even now the pH is around 10.5, it is still too high and I want to bring down the pH to acceptable levels. So, I am going to have second stage recarbonation. So, second stage recarbonation. Here I am going to bring down the pH and also in the process add the alkalinity or increase the alkalinity of the relevant system, and then you are going to have the obvious granular media filtration. Let us move on. Usually for excess lime process, this is something we already looked at. So, if I added calcium, right, in the form of lime, I have to remove that. So, what are the advantages? Because I am using carbon dioxide in the first stage recarbonation, it will reduce some of the soda ash dose, higher calcium removal. Yes, that is something to keep in mind, right. So, let us move on. Split flow. Well, I guess there are different reasons to choose it, but again you need a lot of control on your particular system to be able to achieve the relevant objectives with split flow. So, here one aspect to note is that compared to the two stage, here I am not having two stages of carbonation, I only have one stage, right. But all others are more or less similar except for this particular bypass. Portion of influent bypasses the first stage, right. So, let us see why. So, here I added excess lime to remove calcium carbonate and magnesium hydroxide. This is similar to the case of two stage, let us see. And then I come out here, I want to bring the pH down. So, I added carbon dioxide in the previous case, but here I am going to use the bypass or the raw water here, right. So, that is something to keep in mind. So, pH down, and also if there is enough carbonate in the relevant raw water, that will also add to the relevant alkalinity or the CO3 2 minus, and the additional required you are going to use soda ash, right. And then the carbonates. So, assuming that the pH is maintained at the right condition, CaCO3 is going to precipitate out. So, after this stage you have 2.5 or 10.5, pardon me. So, carbon dioxide is going to be used to bring down the pH, right, to acceptable levels of 8 or 7.5. So, split flow, that is the major aspect, but simultaneously you can have other systems like RO or ultrafiltration and such. I believe we are discussing that now, right. So, two or more streams, right. One aspect was it is coming in like this, and there is also a bypass, right, bypass to that excess lime treatment initially. That is something to keep in mind. It to various degrees, they are treated to various degrees with different process treatment techniques, and then you can blend it. For example, I do not need to treat everything to the same extent. If by mixing, let us say 2-3 different streams, I can achieve my effluent quality that is desired without having to spend a lot, right. So, that is the relevant principle here. So, there are different split stream configurations, 3 split stream configurations, I guess. We can have parallel softening and coagulation, parallel lime softening and ion exchange or reverse osmosis, right, which we are going to discuss later. Split treatment with excess lime, let us see, right, different configurations, but you do not need to obviously mug them up, but I am just mentioning that out here, right. So, this is something we already looked at in the context of that example in the last session, but we just are going to look at the overview, let us see. So, single stage, right, and what is it for? When low magnesium and high calcium and carbonate hardness associated with carbonate hardness, right. So, I am just going to add the relevant lime. So, how much lime should I add? Here they are talking about lime. In general, when we talk about lime, we are talking about the slaked lime, CaOH twice, right. Rarely will you directly add CaO, which is lime. So, carbonic acid and then calcium carbonate hardness, that is it, and Na2CO3 none. Excess lime, right, here we are trying to remove waters with high calcium, high magnesium and enough carbonate hardness, but not a lot, let us see. So, how much lime are we adding? We are adding enough to remove the relevant what is this H2CO3 or carbon dioxide concentration, then the alkalinity, I guess, to increase the pH, yes, and magnesium hardness and excess lime dose, let us see, right. So, that is something to keep in mind. Yes. So, here we are removing the hardness associated with HCO3 minus or the carbonates or the bicarbonates, that is what we are achieving here, while also increasing the pH, and the magnesium that is not associated with the carbonate hardness, I guess, and then for excess lime dose, let us say, right. But I guess depending upon the extent of lime dose, you are not adding Na2CO3, but if it is very high and if you are adding excess, then you will have to add Na2CO3, let us say. But that is not the case here, because we are assuming that there is enough carbonate hardness. So, same case here, single stage lime soda, right. So, this is just single stage lime, this is excess lime. So, single stage lime soda, right. Here we are also adding what do we say, soda, one set of lime or fraction of lime to remove the carbonic acid, the other for removing the calcium carbonate hardness. Then Na2CO3 for removing the calcium non-carbonate hardness and or magnesium non-carbonate hardness. Again, this is just getting repetitive, but this is one way for you to look at it. So, let us look at the equipment, let us say, right. So, conventional, which is reliable but typically more costly, we looked at it in the context of the sedimentation basins with respect, I think, the wastewater and even with respect to water treatment, right. So, what do we have? We have a rapid mix initially, right. You want to mix the relevant coagulant or flocculant, right, coagulant, pardon me, pretty well, and then you have flocculation basin where you have relatively gentle mixing for a relatively higher or more time compared to the coagulation basin or the rapid mix basin, let us say. And we looked at this horizontal paddle wheels or vertical turbine or common, let us say. And then we will look at sedimentation basin, where obviously we need to give much more time for the relevant particles to settle down, let us say, right. Solids are recycled from the sedimentation. Why is this? It increases the particle size and increases the removal kinetics. Why is this? In precipitation, we have different steps starting with nucleation, right, and here the trigger has to be that it has to be super saturated, saturation has to be greater than 1000 or 100, let us say, right, and then crystal growth, agglomeration and so on and so forth. So, here we have surface area to be in the second step, we will have surface area limitation and also depend upon the level of saturation. So, if you add some or recycle some of the settled sludge back to the relevant process here, let us say, you will be increasing this surface area or the area available for the relevant crystal growth to take place, let us say. So, in that way you will increase the removal kinetics, right, that is something to keep in mind, that is with respect to precipitation. So, upflow solids contact basins seem to be common. So, upflow here with radial weirs, right, these are the radial weirs, and how are you going to scrape the sludge at the bottom? So, here you have the scraper arm and this is obviously the basin floor, this is the basin floor. So, this is one blade and obviously another one which is flexible enough to handle this circular perimeter, let us say, right. So, that is why you have this kind of an setup. So, second stage upflow solids contact unit and you see the radial launders, let us say, right, radial launders. Some are along the periphery, some are radial launders. Upflow solid contact basins. So, lesser size and number of basins result in lesser capital cost, let us see, right. Effective solid contact units draw the settled precipitate from near the floor and then recirculate it with the incoming water, and in the previous slide we looked at why we are doing that, right. So, this is a typical system, right. So, raw water is coming up, upflow, right, and then what do we have? Hood or skirt, I guess, mixing out here and sludge scraper at the bottom. So, the relevant supernatant is going to be collected in the launders, which we looked at earlier, let us say, right. So, that is what you see out here. So, it is coming up here, yes, and then flocculation is taking place out here, I guess, right, and this is the separation zone. This is relatively clear, and this sludge blanket, part of which will be scraped at this particular bottom, right. You have the sludge hopper and it will either go to disposal or some of it will go for recycle, right. So, that is what you have out here. So, you have the mixing out here and also the flocculation setup out here, right. Let us move forth. So, equipment, you have solids concentration to be 10%, different sources give different what do we say, piece of information, but this is an acceptable range, yes, and this is from Mackenzie Davis if I am not wrong. The mean velocity gradient gives you an idea about the level of mixing, and g theta, right, this is a relatively high value and this is for theta, let us say we are talking about, I guess, the sedimentation basins here. So, until now we looked at water treatment, right. What did we do? We removed suspended solids, we looked at disinfection of the relevant pathogens, and then we started looking at specific aspects. If my water is hard, especially if it is groundwater, what is it that I am to do? How will I go about it? So, in that case we looked at using the principle of precipitation. If I increase the concentration of the relevant ligand, which is OH minus or CO3 2 minus in the context of hardness removal, I can use them or use that particular, what do we say, chemical or environmental chemistry background to be able to precipitate out Ca2 plus as CaCO3 and Mg2 plus as magnesium hydroxide. So, that is the principle we used. So, there will be some compounds which I can't remove by precipitation, right. For example, natural organic matter, or let us say there is other organic matter which is aromatic in nature, right, aromatic in nature, let us see, right. Or you have aliphatic compounds, again let us say they were not removed during your water treatment process and such. So, I want to be able to remove these relatively trace concentrations of organic contaminants, organic compounds, which might be toxic to me or which might create nuisance or which are not at acceptable levels. So, here we are going to use a different principle. The principle is that I am going to have a media, right, and this will be able to adsorb. The key aspect is AD, adsorb. We will come back to look at what this is, adsorb, right. It will be able to adsorb this organic matter or these organic matter or that organic matter which is hydrophobic. So, we are looking at a couple of terms here. One is adsorption, and the kind of compounds we are trying to remove are typically hydrophobic. Phobic, phobia, right, fear, they do not like it, I guess, hydrophobic. So, hydro water, phobic, those compounds which are hydrophobic, and we are trying to achieve them by adsorption. So, in the next 2 sessions we are going to look at adsorption. Let us move forth. So, definition. First aspect is to be aware of fine difference, but considerable importance. So, one is adsorption, the other is absorption, right. What is the difference? Let us see, I think I have a picture later that should be clearer, but let us look at the definition. Again, do not need to mug up anything, but you need to understand the relevant aspect. So, adsorption, AD, is accumulation of molecules. Keep in mind it is accumulation of molecules, fine, but where? On the surface which is in contact with the water phase. At least for our case we are talking about water phase. We are going to have a surface, a media, let us say, and the media can be activated carbon, right, and that is your surface, let us say, and here we are talking about removing contaminants from the water. So, I will not look at here, yes. So, that part of the activated carbon that is in contact with the water is the surface, yes, and my particular molecules of interest are going to accumulate on the surface. Why? We will look at that later, but the principle is that they are accumulating on the surface. The other one is absorption. So, absorption meaning it is more or less dissolution of molecules within a phase, right. For example, if water is there and I add sugar, right, it is not going to, the sugar is not going to stay on the surface, it is going to be absorbed in a way that is not a great example, and then it is going to be dissolved, dissolution, let us see, right. So, that is dissolution, it is not on the surface. So, it is dissolution of molecules within a phase. For example, an organic phase in contact with an air or a water phase, let us see. So, then you can have relevant compound that will stay both in the air and also your relevant solvent phase, let us say. For example, if I have a scent bottle and I open that up, the compound is pretty volatile. So, it is going to now, what do we say, change phase, some of it, and it will be in 2 phases. One will be in the gaseous phase, one in the solvent or the aqueous phase, depending on the kind of solvent or scent bottle that you have. So, general term sorption, that is the relevant term that is going to encompass both adsorption and absorption. So, adsorption is on the surface, absorption is into the interior, let us say. So, this is within a phase. Let us look at the picture, okay. So, adsorption, let us say, I have a compound here, right? Initially everything is present in the relevant water, let us see, and then I add my media, let us say this is my media, and some of it is now adsorbed onto my surface, it is adsorption, right. So, as you see it is adsorbed here, one is in the bulk phase, right, bulk liquid, right, and the other one is the other phase where it is adsorbed, it is called phase I guess, but it is a bit tricky to call it phase because we are talking about accumulation on the surface. The other one is absorption, right, absorption as in one will be in the water, the other one can be in the solvent, or one can be in the air, one can be in the solvent. Here it is not on the surface, but within the phase, let us see, that is why it is absorption. One example obviously that is mentioned is Henry's law, which gives us the relationship between concentration in the gaseous to the concentration in the aqueous phase, right. So, there I guess we are not talking about adsorption, but dissolution into two different phases, right, that is something to keep in mind. So, with that I will end today's session. In the next session we will look at adsorption, what drives adsorption, what kind of media do we typically use to, what do we say, achieve adsorption, and what are the compounds you can typically remove, right. So, that we will get it done in the next session. Thank you.